All right, everyone. So welcome back to the afternoon session. This clock is a little slow, but you have to look at that clock. So I'll split the difference and start 1 minute early. Anyway, this is Mississauga's own Pawel Sarkowicz, who will talk about unitary groups, K-theory, and traces.
Thanks. Yeah, I forget which hospital I was born at, but apparently I was born at 6:25 and 6:25, like June 25th at 6:25 in the morning. But my mother might have lied to me. It wouldn't be the first time, so actually that might have been the first time. It wasn't the last. But yeah, we're going to talk about unitary groups, K-theory, and traces. Here's a brief outline. A panorama. Panorama, the sound. You can just put any vowel there, can't you? So panorama, 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 panorama of unitary group isomorphism results. You could put any of them. I put an A because English is my first language. Actually, Polish was. I found out in grade 12, and they said I was ESL, English second language, after I'd finished high school. I was really confused. Anyway, we're going to talk about a weird view about K-theory, and then we're going to relate continuous group homomorphisms to K-theory and traces. So, here's some notation. The unitary group of a C-star algebra is just all the unitaries. So all the U's satisfying this. Here's some more notation. UN of A is going to be, well, the unitary group of the matrix amplification. And if I put an O there, or a 0, yeah, this is the things connected to the identity. Right? It's a unitary, or the unitary is from a topological group, right? Take the norm topology and you restrict. And you could think about the connected component. And I think I'm just going to leave that board like that now. But yeah, so let's do the first part, a panorama of unitary group isomorphism results. So people have been classifying C-star algebras using unitary groups for a while. So here's some theorems. The first one is due to Dye in 53. I referenced the paper and it says 53 in the bibliography, but if you read the paper, it says 52. Anyway, so if we take finite non-atomic von Neumann algebras, then, well, the unitary groups are isomorphic if and only if the algebras are isomorphic. And you got to be careful what kind of isomorphism you're talking about. This one is a bicontinuous with respect to the weak topology group isomorphism, and this is a star iso either linear or conjugate linear. So this is the first kind of result like that. And now I'm going to list a bunch more. And maybe this will be boring, and that's why it's only one part of the talk. Does this board go up? Oh, wow. Another result of Dye. I'll be less formal about this one, but unitary groups of factors. So let's forget about the topology. They determine the type. Cool. Yeah, that's not too specific, but that's okay. This next one is due to Sakai in the same year. Well, actually, again, if you read the paper, this one says 54, and then in my bibliography it says 55. I blame Math Scinet or someone. I don't know. It's almost 100 years ago, so maybe I'm the only one who'd complain about something like that. Because 100 years seems like a long time. Having a post-midlife crisis right now. 28, went skydiving a couple weeks ago. I think K-theory is a lot like skydiving. I'll tell you about it later. So if we take M and N to be AW star factors, and if we take phi to be M's and N's are hard. Phi to be a one-sided, uniformly continuous, so uniformly with respect to the norm on these things, continuous group iso, then M and M are the same star isomorphism or conjugate linear star isomorphism. Okay, and this is the kind of result that I use the same techniques Sakai does, and I apply them to K-theory. So these other ones are a bit weird to me, but, well, they're not weird. They're just not what I did. Yeah. Okay, and then there's a theorem of Yen in 56, which some variation for M and N general AW star or von Neumann algebras. AW star algebras, not von Neumann algebras. And by some variation, I mean they're AW star algebras without type 1n things, and you get a similar result. Cool, and I'll leave it like this for the von Neumann type classification. There's some C star stuff too that I'll get into. So the first one is Patterson in 85, 83. You know, years are kind of a big thing for me, apparently. I save my files and I write the name of the paper, and then I write last name and year. I had this saved as Patterson 80, and I was really confused when I opened it up, and it was Patterson 83. But it's 83. It's 12 years before I was born. Wow. Oh, if you're born in 83, you're 40. Anyway. So if you take AB to be unital, C-star algebras, oh yeah, wow. Then A is isomorphic to B if and only if the unitary groups are some strong notion of isometrically isomorphic and identity on the circle. Right? It's you got a group homomorphism which sends X the identity, X as the identity on the circle. Right? A's got a unit, it's got a copy of the circle. B's got a unit, it's got a copy of the circle. Cool. Okay, and now there's probably some more stuff in between. I don't know, maybe not. I've tried to, read stuff, but reading's hard sometimes. So I'm sure I'm missing some, but. So this one's more recent, in 2014. This one says, if this is the same in some sense, if and only if A is the same in some sense, so what's the sense? So this is Jordan star isomorphism. And this is, well, surprisingly, who cares about the algebraic structure? You just have an isometry between their unitary groups. Okay. Point is, unitary groups have a lot of structure. Here's more structure results type things. Wow, I'm already back to. first board. Oh. So there's still theorems. I didn't realize how many I listed because I just listed them without numbers, but now I realize there's at least 7. There's at least 1, but there's more than that too. So this one is T.A. Giordano's there. Him and some people. I'm not going to try to pronounce this name. Rawashte, Booth, and Giordano. And this was in 2012. So at some point I was going in chronological order. Wow, I remember that word. I was thinking of what it was earlier. Anyway, I've stopped the chronology. They classify some, not write the words because maybe they're, I'll write the words. So unital AH algebras, simple, slow dimension growth. Of course, my adjectives are out of order. Slow dimension growth should follow AH algebras because simplicity and slow dimension growth don't have anything to do with each other. That's okay. Of real rank 0, then topological isomorphism actually gives star isomorphism. And it's 3 and 7 that are kind of what I'm going to do things similar to. Sakai uses some variation of, or just uses Stone's theorem at some point, and I use that. And then this is a K-theoretic classification. And there's a second part of this, and it's just purely infinite, simple, unital. I think you need UCT, nuclear, then algebraic isomorphism. If and only if the algebras are star isomorphic. Okay. And the list keeps going for one more time. So semi-recently, by that I mean this year. It's been a long year, so I don't know, semi-recently. I get that it's October, and there's still 2.5 months, 3 months, 2 months, 3 months. Anyway, so in 2023, Lionel Robert and his student, I believe is a student, Takutsing, which I'm not saying right. And I forgot the first name letter for everybody else. I don't know why I wrote it here. Anyway, this is in 23. And they just show A, B, unital, prime, with no 1 or 2 dimensional representations. Then their unitary groups are topologically isomorphic, if and only if their connected components are. And this is if and only if A and B are isomorphic as real C-star algebras. And there's another condition here. Lionel Robert has introduced a special unitary group, and there's an isomorphism there too, but I'm not going to introduce it, so I've skipped that one. Yeah, wow, I'm running big, I guess. And I'll finish off with this one, just as motivation about why traces is in the title. So I guess 9. And then Chand and Robert, also this year, which, wow, this year's a weird year. be cool to be born in 2000, right? It'd be so easy to know how old you were. Anyway. So unitary groups of, well, unital prime traceless C-star algebras, their connected components correspond to a star iso or a anti-star iso. And also, in the same work, they show tracial C-star algebras admit discontinuous unitary group automorphisms. So mainly because of this, you know, the unitary group isomorphism problem. Really, it's nice when things pass to, like if your unitary group homomorphism is the restriction of a star homomorphism or something like this. And so it's going to end up being continuous. But if these guys don't have continuous maps all the time, I'm just going to assume continuity. Yeah, okay. That's the panorama of unitary group isomorphism results. Point is, they obviously have a lot of structure. And then the third part of the talk, I'll be talking about general continuous unitary group homomorphisms, and we'll say some things. Yeah, so from now on, we'll just say A, B, unital. Well, let's assume their traces, the trace simplices are non-empty, right? You always get a convex set of traces, and if it's unital, it's compact, and it's a showcase influx. But okay, so a weird view of K-theory. It's not that weird. It's just, right. I went skydiving a couple weeks ago. I realized skydiving is kind of like K-theory. So you're like, oh, that's not so bad. And then you get closer to the plane, and you're like, oh, I'm going in the plane, whatever. And then you're not the first one to jump out of the plane, you're like the third. You see the first person jump out, and you're like, ooh, not liking this. And this is like seeing other people's results about K-theory, right? And the second person jumps out, and you're like, oh my God, my heart's beating. And then you go, and you're just falling 10,000 feet, and you're like, wow, this is fine, actually. Until you hit the ground, and you realize that was awesome. Not hit the ground. But a weird view of K-theory. So the classic view of K-naught, if you will, is you take matrix amplifications and you look at projections, at least in the unital case, and you mod out by this Murray-von Neumann equivalence, and then you form this Grothendieck group. But that doesn't help us, because if we want to look at unitary group homomorphisms, I mean, first off, we're not taking matrix amplifications. Second off, what if there's no projections? How are we going to talk about K-theory? So, I mean, there's another view, and I guess it's more of a theorem, I guess. I don't know who. There's a proof in Rorem's book, so it's someone. But the ith homotopy group of this infinite unitary group is just K1 minus I of A. So A is unital here. And what's this? This is just the direct limit of UN of A with connecting maps U going to U1. And so essentially, I is 0 or 1 here. If you look at this stabilized group of unitaries, the K-naught group is the fundamental group, and the K1 group is the connected components. Okay. I forget where I'm at. But why is that nice? Well, because for a lot of C-star algebras, you don't need the matrix stabilizations. So A has a stable rank 1, or is Z stable? One of these work, and this is Riefel. Or Riefel, I don't know. Some people have called me Pawel before, so maybe he's Riefel. I know he's not, but he's Riefel. And this is Jang. If A has this, then this, if you consider the map that takes a unitary into the top left corner, it induces a map between these fundamental groups, right? But the map pi I from U of A, and I should say, you know, if we're taking the fundamental group, it's the base point's the unit. Okay, so the canonical map is an isomorphism. I'm sure there are more classes, but this is nice because if we're looking at K0 and K1 as homotopy groups of the unitary group, and you know, I guess the end goal is get some map in some semi-functorial way, it's not quite functorial, between L invariants. You want to get maps between K-theory and traces. Well, you get the K-theory for free if you just assume one of these things on either of the C-star algebras. So we're going to do that going forward. Well, not quite, but we'll assume that eventually. Okay, so that gives us K0 and K1. And I guess the image of the unit's important, right? What's the image of the unit if we look at this? Well, this isomorphism comes from if P is a projection, then the map which takes T to this loop, this induces this isomorphism. So what's the image of the unit? Well, it's just e to the 2 pi I t. Yeah. So we've got the image of the unit, and we just have to worry about traces. And maybe this isn't that weird a view, but there's a pairing map. Rho A from K0 of A to the affine functions on the trace simplex. So this is continuous affine functions from T of A to R. And for a lot of C-star algebras, if you just have K0, image of the unit, K1, the space off T of A, and this pairing map that determines the L invariant. But how on earth are you going to get this pairing map? So it's defined if P or if PQ are in the same level, then rho A of P minus Q of a trace tau, right? This is a function on the trace simplex, so it's applied to a trace. This is just going to be take matrix amplification tensor with tau of P minus Q. And so how do you get this from your homotopy group, from your fundamental group? Yeah, I feel like I screwed up the board order. That's okay. Well, there's a solution. I mean, not that that was my problem initially, just I have other problems. They're just not math related, but mostly self-inflicted. Anyway, so how do we get the pairing map? Related to algebraic K1, we won't talk about algebraic K1, but Delaharp and Skandalis defined this Delaharp-Skandalis determinant. I guess they didn't call it that. Everyone else calls it that after them. Did George name the Elliott invariant? I don't know. Anyway, but they didn't call it that. We call it that, but it's this C-star analog of this Fugly-Cadison determinant. And let me justify it to you in some sense. You can actually write for x in GL naught, let's do unitaries. Oops. So in the connected component of C, actually you don't need this. The unitary group's connected from C. Right, that's Mn is a von Neumann algebra, so if you pick the unitaries, you can take a logarithm. Anyway, you can write the determinant of x as e to this weird integral, trace of some path, dt, where c is a path from 1 to x, and it's piecewise smooth. It doesn't need to be piecewise smooth. I mean, if it is, if you want to define that kind of integral, but everything's homotopic to a piecewise smooth path like this, and you could do this. And so they use this kind of trace applied to derivative. Sorry, there's an inverse. And I mean, you could convince yourself by saying, you know, if I have a matrix, it's of the form e to the a, and you could just take the path e to the ta and see what happens. You're going to have some scaling factors of 1 over 2 pi I somewhere probably. But if you just take this path, it's piecewise smooth. The derivative is a times e to the ta. So you multiply by the inverse, and wow, the e's disappear, and you get trace of a. Okay, so in general, for a unital, I'm going to call this the predeterminant let's call it at the nth level is a map which takes a path, let's say piecewise smooth, C from 0, 1 to the unitary group. And so here n is going to be either natural or infinity, because we can work in this amplification of u infinity. And then how is it defined? Well, it's not that important, but it's a little important, I guess. It's going to be a map when it's going to take a path and integrate it in a certain Banach space. It's going to take so this is going to be the integral of trace of A. So the trace of A, this is actually a quotient of the self-adjoints. And it takes A to this map A hat, where A hat at tau is just tau of A. And it's a tracial map. You can realize F_t of A is the set of all self-adjoints mod the ones that vanish on every trace. Anyway, it's not super important. I'm missing 1 over 2 pi I. And it looks like a mess, and it's not super important, but it has some nice properties. It's homotopy invariant. And so in particular, every path is going to be homotopic to a piecewise smooth one. So forget the piecewise smooth thing and just define it on all paths. Sends products to sums. And, well, I should say what this is an element of F_t of A. Okay. Right, this is just the Riemann integral. So it sends products to sums. And if x is in K naught, then rho A of x is actually just equal to this predeterminant of x, well, let's say Cx, where this realizes x as a loop. So we've recovered our pairing map somehow from this predeterminant. Okay. This is maybe why I say it's a weird view of K-theory, because when you view K-theory the first time, you're like, I could compute K-theory of C. Right? You know, you look at matrix amplifications, and oh, if the ranks of these projections are the same, they're the Murray von Neumann equivalent. You take the Grothendieck group, you get Z. Wow. But if you ask me to compute the fundamental group of the circle, I forget. Anyway. Homotopy is hard. That's my point, I guess. And maybe trying to do something in a homotopic kind of way is silly if I don't know how to compute the fundamental group of the circle. Yeah, I know what it is. I could look at a space and tell you the fundamental group. I'm not well versed in topology techniques. Begs the question of why I was doing this. But anyway, cool. Wow. Okay. Who cares? I do. Someone does. I hope. Maybe. Cool. So with this, I mean, we'll move on to the third part. Because we sort of have all the information to get maps between Elliott's invariants, right? We have the fundamental group. Well, if you've got a continuous map between spaces, it induces a map between fundamental groups. If you've got a continuous map between spaces, induces maps between the spaces of components. What's this? Pi naught. See, I'm not a topologist. I'm not very topological, which I was thinking about the word topological as an adjective, and it doesn't describe me very well, because I'm a human being. Anyway, okay, so going forward, wow, it's all the bad jokes. Going forward, let's take theta to be some continuous map or continuous group homomorphism. So for free, theta induces pi I of theta between the unitary groups. So we've got a K1 homomorphism and we've got a K0 homomorphism. The problem is that if theta is truly anything, it's not going to preserve the unit, and then this map I'm going to define on traces in a second isn't going to be unital and positive. But we'll do some things. So I'll start with maybe a tidbit of why I would even hope to get a map between affine functions on the trace simplex. Of course, once you know how to do it, it's super easy, and you're like, well, yeah, obviously you get one. But I'm not the brightest, and I certainly wasn't when I did this. I was even less bright. So I didn't know why a map would come about things. But there's this theorem of Thomson, and it says if you look at the connected component and you look at this, which is the closure of the derived group, du, so the group generated by commutators, then this is topologically isomorphic as a group to af t of a mod, and you could put n's and stuff here if you want, but I'm only interested in the one case. But you take af t of a and you mod out by this image of this predeterminant of this fundamental group, which again, it's closed under it's homotopy invariant, so I have no problem saying the fundamental group. Okay, but if I've got a B or another C-star algebra and a map, which is a continuous group homomorphism, it's going to induce a map here, right? Because theta is a group homomorphism, so it sends commutators to commutators. And I mean, it's continuous, so it's going to respect closures. So we've got a map between quotients. But then this is also just, of course, this is Thomson's theorem, and this is, the rest is, af T of B mod this. So we get a map for free, just, but these are quotients of af T of A and af T of B. And of course, the map I want to end up having is going to be a lift of this. Say, of course, I mean, maybe it's not that, of course. Okay. Anyway, so let's write a theorem and then do some examples, and then write another theorem, maybe. So let's write a theorem. AB unital theta, a map between their unitary groups. I mean, we could just take the connecting components. Then there exists some map. Let's call it lambda theta. Or linear bounded, but I'm not going to say all those other words I said about unital and positive because they're not true. Such that, well, this map when we look at the predeterminant to af T of B, let's call this map lambda tilde innocuously. So this diagram commutes, and lambda tilde or lambda theta is a map of the tilde map or lift of it. Okay. But in particular, when I take C-star algebras where everything's nice and the predeterminant is the repairing map and the fundamental groups are my K-naught groups. So I'll just say AB nice. This implies K-naught of A to K-naught of B to rho B af TB af TA commutes, and this is just still pi 1 of theta. Of course, you know, we've got to compose with some isomorphism. And this looks like, you know, if you, the new view of K-theory and traces is you detect positivity by having maps where this diagram commutes. But this map on the right has to be unital and positive. And it's not always, so let's talk a bit about that. And then I'll give some sufficient conditions for it to be unital and positive. And at the end, I'll just use magic classification to say, wow, some unitary subgroups correspond to subalgebras. Cool. Of course, classification isn't magic. The only thing that's magic is politics, because it's always dumb. Like anyway. Okay, so remark, this is not always unital positive. But, you know, you can make it unital positive sometimes. I mean, here's some examples. If you take, I think Danners, who gave me this example once, maybe. You take 3 elements on the circle, and you map it to x, y, z. The map, of course, this is just the unitary group of c to the 3. And so when I take the affine function on the trace simplex, it's going to be r to the 3. And it's just going to be x, y, z. Of course, using x, y, z for unitaries and real numbers, but hey, I'm not perfect. And so this isn't going to be positive, it's going to be unital. And one can cook up other examples, but there's a, I guess I'll write them. Wow, I still have time. Yeah. This one's not positive. And of course, you know, I'm writing finite dimensional examples because, I don't know, good luck writing a like automorphism of U2 even, you know. These are all trivial, but they give some insight, I guess. If you take, well, this could be example number 2, take theta from just the circle to the circle, I don't know, z to z to the n. Well, the map lambda is just going to go x to nx. And so it's not, well, it could be positive, but it's not going to be unital if n is not 1. Yeah. But it could be positive. Okay. Yeah. There are some sufficient conditions, though. And I'll say these sufficient conditions aren't everything. You can even cook up examples where this map is 0 and you still get some sort of nice thing. But there are some sufficient conditions on theta to make unital plus positive or negative theta. One of them. It's positive up to a minus sign, which, if you think about it for a second, all real numbers are positive up to a minus sign, except for 0. It's not positive. Anyway, it depends on your conventions. Does positive mean non-negative, or does?
0 is a positive element of the system.
Oh, that's true. And you know what? Yeah, every real number is positive up to a minus sign. 0 is just positive up to both signs. Okay, so, you know, theorem, I guess. Theta, maybe this one's a bit of a weird one to assume, but if you think about it, you know, you'd like theta to be the restriction of a star homomorphism. Of course, it doesn't always end up being it. Sometimes you get unitary groups that come from sums of star homomorphisms, anti-star homomorphisms. But I'm saying let's restrict to one of them. If you restrict to one of them, theta is contractive, right? Because a star homomorphism is and an anti-star homomorphism is. Sends the circle to the circle. Let's just write equals. And oh, what's my other condition? Ooh, does something. It's injective. Then So either lambda theta or it's negative is unital and positive. And I mean, the way that happens is, well, if the circle gets sent to the circle and it's injective and it's contractive and you restrict to the circle, you get, this restriction is going to be Z or complex conjugate. And that's where the 1 or the -1 comes from. I mean, it sucks to assume these things, but hey, it works. And in particular, AB nice, so stable rank 1 or Z stable, you have that this map, and I'm gonna write positive minus theta. So minus means if I take a loop, I'm gonna flip the orientation. So this whole thing commutes, and the map on the right is unital and positive. So plus or minus, and this whole diagram commutes. So this is going to send the identity to the identity, and we have this commuting diagram, so we get maps between K-theory and traces. If we assume these conditions, contractive, circle to circle, and injective. And I suppose that's maybe I started off with this panorama, and they were all surge activity results, if you were. Maybe that's why I think this is interesting. Maybe not. Maybe I think it's interesting for other reasons, and I'm lying. Anyway, so a corollary. I make this joke all the time, but I used to not be able to pronounce my R's and L's, so I'd be like, "Hi, I'm Power." Of course, when I'm growing up, and I decide when I get to say I'm Power and Pawel. I often say Powell. Sometimes I'll say Power. Anyway, so if you use this new K-theoretic classification of embeddings, Chris, Stuart, Aaron, Jimmy Gabe, and Jose Carrion. Yeah. They classify embeddings using a bigger invariant than K-theory and traces. So if you look at KTU, this is some K0A, image of the unit, K1A, the pairing, an AF T of A. And they classify embeddings with a bigger invariant. But if you have maps between this invariant, so a map is a set of group homomorphisms with some commuting diagram like this, it lifts to this bigger invariant, and you get embeddings for free. And so if A is, okay, let's do the adjective thing now. Unital, separable, simple. They don't need simple for their classification. I just put it there. Nuclear, UCT, and Z stable, or the stable rank is 1. And B is, okay, unital, separable, simple, nuclear, Z stable. Then the unitary groups embed contractive, circle to circle, and injective, if and only if the C-star algebra is embed. And I'll admit, I'm not saying that theta is the restriction of a star homomorphism, so that kind of sucks. But pass through the K-theory magic. Of course, it'd be nice to get rid of the contractive like that, but it's what it is. And yeah, I'll stop there. So thanks.